In this section, our goal is to be able to solve a system of equations graphically. Let's begin by looking at this situation. A business rents skates and bicycles. They charge $15 per day for the skates and $30 per day for the bicycles. During one day, the business has a total of 25 rentals and collects $450 for the rentals. What is the number of pairs of skates rented and the number of bicycles rented? So notice that they're asking to find two amounts. One is the number of pairs of skates rented. So let's call that X because we want to find that, but we don't know what it is. And the other thing is the number of bicycles rented. Let's call that Y because that's a different amount, and we also don't know what that is. Let's label that X is the number of skates rented, and that Y is the number of bicycles rented. And now let's see how we can relate the number of skates rented to the number of bicycles rented with the other information from the problem. Notice there's numbers about two different types of things. One of the types of things is money. Here's numbers relating to money. We should put all the things that are like each other together. All of the money numbers will go together. And then we have information about the number of rentals. We don't have any other numbers that pertain to the number of rentals, but we know that X represents how many skates are rented and Y represents how many bicycles are rented. So the total rentals would be by taking the number of skates plus the number of bicycles, and it equals 25. Remember that the biggest number will always go on the right side. Now let's look at the other thing about the numbers, the money. $15 per day for the skates and $30 per day for the bicycles, with a total collection of $450. So $15 per day for skates, so 15 times X, plus $30 per day for the bicycles, so 30 times Y, equals, and the biggest number, the 450, goes on the right side. Now, we've solved equations before, but we've never had to solve when we had two equations. This is called a system of equations. And today we're going to talk about a method for solving a system of equations. We'll revisit this problem another time. A system of linear equations, also known as a linear system, consists of two or more linear equations in the same variables. The solution of a system is an ordered pair that satisfies both equations in the system. Remember, satisfies means to make the equations true. An ordered pair is like X comma Y. Let's look at one example. Find the solution to the system of equations by graphing. Here is one method we can use. Altogether, we'll be talking about three methods to solve systems of equations. Graphing will be the first method. So we'll graph both of these linear equations. Let's begin by graphing this first linear equation. Notice that it's in the form of y equals mx plus b, slope-intercept form. B is where we begin, and for this one, the b is -1. So I start on the graph, down 1 on the y-axis. The slope, m, is how we move, and the slope here is 1. So m is 1. From here, we move up 1 over 1, up 1 over 1. Let's plot as many points as we can on the graph such that we have a very nice straight line. Let's take a look at the second linear equation. B, where we begin, is positive 2. So 1, 2 on the y-axis. And then we move the slope. M is 2, or 2 over 1. So from this point up 2 over 1. If I run out of room, I'll go backwards. Down 2, backwards 1. Down 2, backwards 1. Down 2, backwards 1. I forgot to connect the points on the first line. Silly me. Let's do that now. Get out your straight edge so you can connect the points too. Let's connect the points on our second line. Get out your straight edge so you make a nice straight line connecting the points. Now, if the solution of the system is going to be the ordered pair that satisfies both equations, that's going to be the point that's on both lines. Which is the point in this picture that's on both lines? This point is only on the blue line. So is this one. So is this one. But here, this is a point that's on both lines. So we're going to find the ordered pair for this point. From the origin, we have to move left. 1, 2, 3. Negative 3. And then we have to move down. 1, 2, 3, 4. That's negative 4. So the solution is the ordered pair negative 3, negative 4. This is the ordered pair that will satisfy both of these equations. This point is also called the intersection point. The intersection of the two lines is where the lines cross or touch, kind of like an intercept. That's the intersection point. The intersection point is the solution of the system. That's the intersection. When we're graphing, that gives us the solution of the system. Let's take a look at how to verify this answer with our calculator. Let's plug both of these into y equals. Into y equals, I'll plug in y equals x minus 1. X minus 1. Into the next y equals, y sub 2, I'll plug in 2x plus 2, because it's the second equation. 2x plus 2, enter. And then let's graph it. Zoom standard is the best view to see. There are the two graphs. See the intersection point, and now we're going to calculate it. Calculate, second, calculate. Intersect is the fifth choice. Let's go over close to where that intersection is. When we're approximately right on top, notice that it gives us a little guess. It's around negative 2.8, around negative 3.8, but if we press enter, 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 it tells us exactly. X is negative 3, Y is 4. That's a great way to check it in our calculator. Let's take a look at another one. Number 2. Y equals 3. So I only see Y. I don't see Y and X. Remember Hoy, Vux? So Hoy reminds us, because this only has a Y in it, that it's going to cross the Y-axis only, and it's going to be a horizontal line. So we'll find 3 on the Y-axis, and we'll graph the line horizontally. Y is always 3. The other equation, x equals negative 2, goes with Vux. If it only has an x in it, that reminds us that we're going to draw a vertical line. Find where x is negative 2 and draw a vertical line. Where is the intersection point for this system of equations? Right here, there's the intersection point. That's at -2, 3. -2, 3 is the solution to this system. Number 3. This equation is in standard form. Remember how we can graph an equation from standard form? We can use the cover-up method, finding intercepts. So let's take a look at what we get when we make the y term 0. -2x equals 12. Dividing by -2 gives us x equals -6. So we have -6, 0 is the x-intercept. 1, 2, 3, 4, 5, 6. And then let's change that and cover up the x term, or make the x term 0. Positive 6y equals 12. Dividing by 6, y equals 2. So 0, 2 is the y-intercept. And now I can connect the points and graph my line using my straight edge. Let's graph the other line. Y equals -2/3 x minus 1. Now this is in slope-intercept form, y equals mx plus b. The b is -1, so start on the y-axis at -1 and move -2/3 from our point down to 1, 2, 3 to the right, down to 3 to the right. I also should go backwards because that's where the other line is, and I'm supposed to find where they meet. Up 2 and backwards 3. Up 2 and backwards 3. And I'll get out my straight edge so I can draw a nice straight line. Do you see the intersection point? Here it is. That's at -3, positive 1. So the solution is -3, positive 1. Let's take a look at a couple more. Find the solution to the system of equations by graphing. So same thing we did before. Let's begin with this equation that's in slope-intercept form, y equals mx plus b. The b is positive 1, and the slope is 2 over 1. So from here, up 2 over 1. And we'll keep going and go backwards. Down 2, backwards 1. Down 2, backwards 1. And continue. Find our straight edge and connect the points. Now the other equation, which is in standard form, we'll use our intercepts. 2x equals -4. Divide by 2, x equals -2. So on the x-axis, -2. Negative y equals -4. So y equals positive 4 when we divide by -1. So on the y-axis, positive 4. And then we'll graph this. Finding my straight edge, I connect the points. Where do these lines intersect? That's right, they don't intersect. Notice that the green line also crosses at points that we haven't marked, such as right here, and right here, and right here. Notice when we mark those points that the slope of the green line is up 2 over 1. So the slope of the green line is 2 over 1. And remember that when we graphed the blue line, it was also with a slope of 2 over 1. They have the same slope. So these lines are never going to meet. When the lines have the same slope, these lines are parallel. And because they never meet, we'll never get a solution. So there is no solution to this system of equations. What about number 5? Let's graph this one, which is also in slope-intercept form, y equals mx plus b. So our b is negative 4, 1, 2, 3, 4, and our slope is positive 1. So from here, up 1 over 1, up 1 over 1, up 1 over 1, continue until we run out of space, and then go backwards. Finding my straight edge, I can graph this line. Let's write on the side that this one had a slope of 1, or 1 over 1. Now let's graph this line from standard form. 4x equals 16. Dividing by 4, x is 4. So 1, 2, 3, 4. Negative 4y equals 16. So dividing by negative 4, y is negative 4. So on the y-axis, 1, 2, 3, 4. And then we'll connect these points to graph our line with our straight edge. Well, what do you notice? The second line landed right on top of the first line. It had the same slope and it had the same y-intercept. The y-intercept for the green line was negative 4, we see from the graph, and the y-intercept from the blue line was also negative 4. So they have the same everything. These are the same line. Where do they intersect? They intersect everywhere at all of the points on the line. So the solution is an infinite amount. We'll call it infinitely many solutions. So the bottom line, in conclusion to remember, is that parallel lines which have the same slope will have no solution. A system of equations that is from the same line, which means everything is the same, has infinitely many solutions. Let's practice checking if the given point is the solution to each of the linear systems. So remember, to be a solution, it has to satisfy both of the equations. Let's see if this one satisfies the first equation first. Remember, this is x and this is y in an ordered pair. So we'll plug in the y. 2. You know what? Let's write that we're using the first equation. Y equals 2x, so the y is 2 and the x is 1. 2 equals 2. That's true. Now we need to check the second equation. Y equals x plus 1. Y is 2 and x is 1. 1 plus 1 is 2 and 2 does equal 2. Both of these are true, meaning the point satisfies both equations, so yes, this is a solution to the system of equations. Let's look at the second one. Starting with this equation and plugging in the x and y. Y equals 4x minus 1, plugging in the 3. 3 equals 4 times x is 1 minus 1. 4 times 1 is 4, and 4 minus 1 is 3. Does 3 equal 3? Yes, it does. So we know that this point satisfies the first equation. Does it satisfy the second equation? Let's see. 2y minus x equals 6. So 2 times the y is 3 minus the x is 1 equals 6. 2 times 3 is 6, and 6 minus 1 is 5. Does 5 equal 6? No, it doesn't. So even though the point satisfied the first equation, because it doesn't satisfy the second equation, we must say no, not a solution. Take a couple of minutes to describe what it means graphically to be the solution to a linear system. See you in class.